So what we're going to add to that, so you guys wrote down no human error, right? So don't ever tell me that one. Okay? Try not to. Try your bestest not to, then I'll judge you a little bit. All right. What you can use is systemic error. Has anybody heard of that? No? Okay. So systemic error means that it's your apparatus that messed up. Okay? If I misspell anything, you guys have my permission to call me out. So I spell it right. I spelled that right. Don't correct me right now. All right, so systemic error means that your apparatus is what messed up. So what that means is you'd be able to quantify how far off your device is constantly reading something or measuring something. So if your balance is always off by 0.5 gram or something like that, that's systemic error, okay? But you can usually fix it. So it comes out to be precision over accuracy. Does that kind of make sense when we talk about, okay. So, so you have that, or you have random error. Now, random error is more when you have your different data. Some of it's up, some of it's down. But altogether, you can still get an average that's accurate. Okay? So the way to pick random error, or the way to fix random error is you take more data. Right? So especially my people coming from physics, you guys had to draw best fit lines in physics a lot, right? Okay, so you had all your little dots, your scatter plot graph. That was showing random error. If you had a bunch that were up and below and side to side and all that stuff, right? So that was your random error, and your best fit line showed your average hopefully being accurate, and that's what you use for a lot of your calculations. Okay, you guys will have a chance to make one, so if you have never made one before, you will learn this year. Okay, for systemic error with your apparatus, you need to actually figure out how far off yours is from what it should have been, and you just basically label all of your stuff and you fix it. You give it a plus or minus, whatever it is. Okay, so you would just basically fix it that way. So, all right. So those are your types of error. I want you to have that with precision and accuracy. So we've already covered precision and accuracy? Yes? Okay, sweet. How about exact and inexact numbers? All right, cool. Good to know. Okay, so for an exact number, what do we remember from my people who watched the video? What do we remember exact numbers to be? Counting numbers, exactly. Okay? So these are going to be counting numbers. What's true about your sig figs? Do we use the number of sig figs in an exact number for? No. Okay? So they have an infinite amount of sig figs. So all I'm going to write is don't use the sig figs. So don't use any sig fig rules on those. And they don't apply as counting as like if you had all these measurements and then you said, but I have one thing, right? So the number 1, you cannot use it to say you can only go to 1 sig fig for your answer, okay? So don't use it. So don't use your sig figs. And also, what was true about working between like American and metric system? They have to be the same system. Good. So conversions in the same system. Ooh. My hand. This happened yesterday, and it ruined the whole video. So I need to not have my hand on anything. All right, same system. Okay, converting between those. Okay, your inexact number, on the other hand, is going to be more of a measurement, so you'll have decimals in it usually. Okay, it's showing you how precise your device is. Okay. You do use the sig fig rules, okay? Because like I said, it tells you how precise your devices are, right? And you use it for different systems, so conversions between different systems, okay? All right, so with that in mind, when we look down at these are straight from the summer assignment again. Let's just review them real quick. Number of faces, what is that? Exact. Good. Mass of 6 apples. Inexact. Okay. Number of seeds. Exact. That's counting. So if I cut an apple in half, I can count the things. Okay. Number of feet in 1 mile. Exact. And liters in 5 quarts. Inexact. Do you guys have any questions over these? All good? Okay, cool. So you guys do not need to turn the page. I have to turn the page. Okay, so just a review of our significant figure rules. You guys just have problems at the bottom. You're good. Okay. We're going to review these. We're going to write just really short things. Okay. So what you guys are going to write on yours is counting sig figs. So I would write it in that little gap below all those numbers if I were you. Okay. You're going to say non-zero. And then under zeros, you're going to say leading, don't count. Captive, count. Trailing, count with a decimal. Okay? You guys want me to write it for you? I'm seeing a lot of people trying to figure it out. Look. Ready? This. Here you go. There you go. Just write that. Is that better? All right, so sig fig rules. All non-zeros, sandwich rule, leading 0, trailing 0 with no decimal. And what I mean by these last two is they don't count. Okay? And then go ahead and give yourself 2 little hashies or whatever. Make another side. Your math rules for this is when you are adding and subtracting, you're using the least number of decimal places. When you're multiplying and dividing, you are using the least number of sig figs. And you are always following your order of operations. That's what PEMDAS is. So we have parentheses, exponents, multiplication, division, addition, subtraction.
So, least sig figs.
Again, this is your order. Operation. What is the what? Decimal places. Okay. Okay, and just remember, if you have exact numbers, right, don't count those. Don't count exact numbers. So I would add that in under your sig fig rules. Exact numbers don't count. That's an addition to what you guys learned pre-AP year. Okay? So exact numbers don't count. Okay? Okay. All right. Let's go ahead and take a look at our examples that you guys got. Okay? So you've got, yours look a little different, but they're the same. All right, so for the first one, we have subtraction. Actually, show me thumbs up, thumbs sideways, thumbs down. Do I need to go over this? Like, I'm sorry, do you have it or do I need to go over it? That's what I need to see. Let me see. Okay, I am going to skip it for now. I do notice a few people with the thumbs down. I promise I will come see you. Okay, so let's go ahead and skip that. Turn your page. And I'll try to remember to do this with a few of us. This one I'm going to take time to do it. I know people who took physics last year, you kind of don't really need this. Just hang tight. So dimensional analysis, all right? So the biggest thing that I could say about this is it looks like how we set up stoichiometry, and I do recommend you set it up that way, even for the easy ones, because if you practice with the easy ones, the hard ones are going to be a whole lot easier for you, okay? Now, this is just you have two little charts at the top of your page, and they have just a couple things that we're going to use for these questions. And then you do have, what is this showing you? What's this?
Oh, decimal places.
Decimal places to use with what system?
10.
This is your metric system, right? This is your metric system. But yes, you're good. It goes by tens. Wouldn't it be amazing if we all just agreed to use the metric system and go by tens? Like, America, darn it. All right, so metric system is universal, so that's why, and it's the easiest one to convert between instead of, inches and all that stuff. All right, so anyway, back to dimensional analysis. So what I mean by dimensional analysis is you are looking at your units. That's what your focus is. So just like when I taught you stoichiometry, you focus in on your units and the labels of those units. You're going to do the same thing here, okay? So I use the railroad tracks, and what I want you to do is write yourself a little note at the top. I'm going to say units. What was always my rule in stoichiometry? Down and to the right. Exactly. Okay? So we're going to say whoop, units go down to the right. Okay? And then when you go up, so what you have on top of each other is always going to be your conversion. Now, this is important because you guys are going to get to a point this year where you're going to be using the concept of molarity, which is moles divided by liters. You're going to use it upside down, right? You're going to have liters over moles. You're going to use it however you need to use it to make that work, okay? But there's a conversion. So anything per something is always, you can always put it in there, okay? So you're going to do that, and then I would write yourself a little note that you're going to do that again and again until you end with what you want on top, okay? Am I still on the screen? Good, okay, cool. This is what you have. When I say what you have, it's what they give you, okay? And if you are not familiar with railroad tracks, this is the same thing as doing times in a line. So if you learned that way, that's what it is. Otherwise, you multiply going across, and you divide going down. Shortcut with that is push multiply, 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 push equals, and then push divide by each number that's at the bottom. Just keep pushing the divide symbol. You'll never mess up, okay? All right. So, we're going to keep that there. The other thing I want to touch base on with the metric system, I do have this poster over here you guys can see. So if you're ever just needing it while you're taking a test or something like that, just remember that King Henry died by drinking chocolate milk. Yeah. My son, when he first learned how to read, he was visiting me in my physics class, and he was looking at the poster, and he just was like, King Henry, and I kind of knew he was doing that, and he goes, like that. And I was like, what? And he was like, did he really die by drinking chocolate milk? Because I drink chocolate milk every day. And I was like, oh, no, sweetheart, that's just, no. It was the funniest thing. And I was like, it was when he first started learning to read, so it was the funniest thing. All right, so anyway, so that'll kind of help you move your decimal back and forth. Okay, that's the good thing about metric system is you shouldn't have to do a conversion, really. All right, let's go down to those problems that you've got. We're going to try a couple of them. Okay, so your pencil is 7 inches long. What is its length in centimeters? Is there an easy way to do this? Yes. Am I going to do it? No, because I want you to learn how to use your dimensional analysis so that when you get to the really hard stuff, you still use it. Just get yourself used to it, okay? So what you're going to start with is you got 7 inches, right? You never delete those zeros, by the way, okay? They're there for a reason because they're telling you a measurement. Those are significant. Do those zeros count, by the way?
Yeah.
Yeah, trailing zeros with a decimal. Because that's telling you what type of ruler did you use, right? It's telling you how far it goes with the little lines, okay? All right, cool. So we got 7 inches. I'm going to bring words down to the right. So I'm going to say inches down here, and I'm going to do a conversion. Is there a conversion between inches and centimeters?
Yes.
Yeah. So I'm going to put centimeters up here. That conversion is that 1 inch is 2.54 centimeters. So this is an easy one. We're ready to solve. You just multiply across. Could you have done this in your mind? Yes, I'm perfectly aware of that. I see some of you guys being like, ugh, why? Just try to get yourself used to the process. That's all I'm asking. All right, when you got the answer, you shout it out, and we need somebody to second it, and then we move on. 17.8, thank you. Why do we end at 8?
Because we have 3 sig.
3 sig figs, good. We're gonna say centimeters. Awesome. Okay. Okay, the speed limit on the highway is always 55 miles per hour. Actually, no, we're gonna go down to number 8. Sorry, go down to sorry, on yours is Corvette number 8 for you guys?
Oh, yeah.
Yeah? Okay, good. All right, on my page it's gonna look weird. So, we do need to do that one. The Japanese car one. Okay. The reason why is this is a double one, all right? So if you are needing to convert both the top unit and the bottom unit, okay? I just need you guys to be comfortable with that. So I'm just going to show you an example, and then I promise we're going to move on, okay? So we have 55. What is MPH?
Miles per gallon.
MPH.
Miles per hour.
There we go. So we have miles. What does per hour mean? How many hours? 1 hour. You guys have all seen that video, right? Where the girl is trying to, oops. Is that why you told me? Okay, back on track. So we are now looking at your number 7. My bad, sorry. Japanese car advertised as having a gas mileage of 15 kilometers per liter. So we're back on that per, so we can do that again. So what does per mean? 1. Exactly. So we're going to put 1 liter here. So when you are dealing with molarity, right, and you have 15 molar solution, that is 15 moles per 1 liter. You are literally going to write it that way, okay? And that's why we're going to do this example real quick. All right. So from this point, we need to convert both of them because we want to end with miles per gallon, okay? We need gallon to be on the bottom. We need miles to be on top. That's important. So what I like to do is I get rid of my bottom one first. Do you have to? No, you can start with the top one. But I'm going to go bottom. So instead of going down to the right, where do you think this liters goes? Up and to the right. Exactly. So we're going to do that, okay? So we have liters going up to the right. We need to get it to gallons. So there is a conversion straight to gallons. So we're going to put gallon below. And that, you guys don't have it on your page. I had to look this one up.
3.7.
Good.
8, right?
Yes. So 3.78 liters for 1 gallon. Okay? All right. So now I have gallon where I need it. Liters went away. So now I'm going to deal with my kilometers. Okay? Bring that word down to the right. You see that? Okay? And we want to get it into miles. So you guys should have...
We have miles to yards, but not miles to meters.
Okay, so you guys are gonna have to look that one up for me. Sorry. Go for it. Figure it out. How many miles are in a kilometer?
1.1.
No, how many kilometers are in 1 mile? Sorry. 1.6 kilometers? Okay, awesome. Thank you. I used to know that one like 2 years ago. Now I totally... All right, cool. All right, so now I have miles where I need it. Kilometers went away. So we have miles per gallon. So now you just plug into your calculator. And go ahead and once you get the answer, shout it out. Let's get a second on it, and we'll move on. So you multiply 15 times 3.78, push equals, and then divide it by 1.6.
9.38.
Okay, I have now heard a 6 point something, a 9 point something, and 35 point something.
Oh, I did my math wrong.
Okay,
35. Sorry.
so who typed in 15 times 3.78? And then you push equals, and then you push divide 1.6. Okay, what'd you get?
35.6.
35.4. And so we're going to round that down to 35. Okay? All right. Are there any questions on dimensional analysis? You will get better at it. So if this is brand new to you, you will get better at it. Just kind of remember your rules for stoichiometry. It's pretty much the same. Okay? All right, cool. So that moves us on to, you guys have a little chart for classification of matter. I'm on this one. There we go. Okay, that should look like yours. Yours is number 8. Okay. There you go. All right, so the latest Corvette has an engine with a displacement of 6.2 liters. What is this in cubic inches? Okay, so I want to do this because of this cubic part. Okay, because sometimes you're going to have things that have the little exponents on the units, right? So the trick with this one, we're going to say 6.20 liters. Does that 0 count? Yes, good. All right, we're going to bring words down to the right. Is there a conversion between liters and cubic inches that you know off the top of your head? No. All right, so is there a conversion between any type of liters and any type of inches? No. Is there one between liters and centimeters?
No, there is.
What's a cubic centimeter? 1 milliliter, right? 1 milliliter. So I'm going to go from liters to milliliters. We're going to go from milliliters to centimeter cube. Bring words to the right again. Centimeter cube to inches cube. Okay?
Oh gosh.
Is there an easier way to do it? Yes. We're going to do the long way. Okay?
Centimeters cubed to inches cubed.
Huh? Yes. All right. So here, what is 1 liter? What does that consist of in milliliters? 1,000 milliliters. Could I have said 1 milliliter is also 0.001 liter?
Yeah.
0.01? One more 0. Okay. Yeah. You can do whichever one you want. Okay. I then told you 1 milliliter is for sure 1 centimeter cubed. What is the conversion between centimeters and inches? 2.54. So we're going to say 2.54 down here. Oopsie. But the kicker here, I just said 2.53. I'm so sorry. I think I'm tired. All right. Is that the cube goes around the whole thing. And that's what matters here. Okay? So 2.54 centimeters is 1 inch. So we're going to do that. So plug that in. All right, so looking at one more of these dimensional analysis, okay? This one is a, nope, not that one. Where is it? Let me see. Where's the one that does, oh, go back to number 7 on your page, sorry. Look at that, okay? If you need help with number 9 on your page, by the way, that's on the video for the summer assignment. Just look at that, it's just a proportion. We're gonna focus on this right now for a second though, okay? So, we know that matter is split into mixtures and pure substances. So if you need to make it a little bit bigger on your page, you can just kind of write it over it. Mixtures, pure substances. Know that your pure substances are split into elemental versus compounds. What's an example of a compound? Common compound, pure substance. Huh? HCl. Okay, yeah. I was going for like water, but...
Yeah, I said H2O.
Oh, okay, that's cool. But yes, HCl is also a pure substance. Oh, NaCl. NaCl, is that really... Is that a pure substance?
Oh, wait.
Mm-mm. We're going to get to that one in a second. All right. And then atoms. Do your diatomics count as elemental or compounds? Diatomic molecules. They're elemental. Good. Diatomic. So people who are not familiar with your diatomic 7, you have a poster back there, a big green poster. Those are your diatomic 7. You also have this little one right here that says super 7. You need to memorize those. What those diatomic 7 consist of are the guys on the periodic table that naturally have to occur diatomically, meaning there has to be 2 of them. So all of your little halogens, those guys, since they're like gases, they have to always be teamed up, right? CO2 and all that good stuff. Okay? You make a little 7 on your periodic table. Starting at nitrogen, go down. Okay? Cool. All right. So diatomics are counted as elemental. Okay? So something like O2 or H2. All right. Okay. Over on the mixture side, you have heterogeneous versus homogeneous. What do we also call homogeneous mixtures? Starts with an S. Ends with the elutions. Yeah, good. All right, there you go. That's when you know I'm losing my patience. I'm just kidding. S ends with elutions. Yes, good. All right. So homogeneous is what we call solutions. So when he mentioned NaCl, like salt water, right? That's what we're talking about. Anything that has a solute and a, what's the other thing called? Solvent, right? Or anything that is diluted also counts. Okay? That's what you're thinking of. So, when I talk about the dilution, you can either look at rubbing alcohol or you can read your parents' liquor cabinet and look through all those percentages that they have, right? So, different amounts of alcohol with water, right? So, that's your homogeneous solutions or mixtures. Heterogeneous. What are your 2 types of heterogeneous mixtures called? Suspension and colloids. Good. So colloids are heterogeneous, but they look homogeneous, and that's the special thing about them. Which one of those 2 gives off the Tyndall effect? Colloids. Good. Does anybody need me to tell you what the Tyndall effect is?
I forgot.
Okay, so that's where you, if I were to hold up a flashlight to a colloid, you would see the beam all the way through. Yeah, because if you hold it up to just pure water, the beam will be here and at the end, but you won't see it through. A suspension, you'll see it as long as it's stirred, and then colloid, you'll always see it spread because it's hitting all the particles. That's why you don't drive with your brights in the fog. No, you're not supposed to. You're not supposed to. All right. Please don't. All right. What do you guys have next? Particulates. Oh, okay. So look at those real quick. I'll tell you what I want you to get from that. The main thing is you have to be comfortable with this. This will for sure be on your first test. I'm going to have you draw something that's actually going to be on the next page that we're going to look at. But be familiar with what your solids, liquids, and gases look like. All right. So your solids are going to have a lot of structure. Your liquids are going to be more like everything turned different ways, loosey-goosey, but they're still pretty close together. And then gases is when you actually have a good amount of space, okay? So just keep that in mind. So you guys have this page on the other side. Flip your packet over. Okay. So the main ones I want to point out. So A, is that showing a pure substance or a mixture?
Pure substance.
Pure substance. Okay, and I would honestly go home and practice all these again. I think you had a few on your summer assignment, but I would practice them again, okay? I'm not going to go through all of them. B, is that a mixture or pure substance? Mixture, good. All right, is B a homogeneous or a heterogeneous? I would say hetero as well, because you have distinct layers, right? Versus something like N. N is also a mixture, but is that homogeneous or heterogeneous? I would say it's homo because they're all going to be spread out throughout, okay? All right, let's look at states of matter. For B, what do you guys think these guys down here are? I would say liquid because they're not totally structured. When I see a solid, I'm thinking these guys or these guys. Do you see that? Okay. So I would say up in letter B, these are liquid. What do you guys think looks like water molecules? What do you think those are? I would say gas. So what is going on in this picture? Boiling. So let's use the right words though. Evaporation. And what would it be if it was actually going the other way? Condensation. Good. All right, let's look down at O. So if we're going from a solid to what's going on up here? A gas. Okay. I just caught that. All right, so down here on O, if these guys are solid, those guys are gas, what's happening here? It's the same compound, so what is it? Starts with an S. These things go underwater. Submarines.
Sublimate.
Sublimation. There you go. This is sublimation. What's the opposite of sublimation? So what if it was going from a gas to a solid? Starts with a D. What is it? Deposition. Is that what you said? Okay. Okay. All right, deposition. So this, remember, deposition is what's in your freezer, the frost in your freezer. Sublimation is going from your solid to a gas. So if you ever saw the iodine does it pretty quick. It's like purple smoke. It's pretty. Did I not show my classes that? I don't know. Okay, well, I will show you this year. If you've never seen purple gas, I'll show you that. Purple, it's pretty. Okay. Okay. Yeah, no. I'll show you this year. Hey, is there any of these pictures that stand out to you that you really don't understand what you're looking at? F? P? P. All right. Looking here, would you say solid, liquid, or gas? I would say solid. Is this an is this a mixture or a pure substance? It is a mixture. How would this have been maybe a pure substance? If they were connected, exactly. It would be a compound pure substance if they were connected. But we have distinct atoms that are separated, and they happen to be in solid. So this is definitely a mixture. And homogeneous or heterogeneous?
Homo.
I would say homogeneous. Or homogeneous. Homogeneous. There you go. All right. And it's elemental. Or, yeah. Is that what we're supposed to say? Yeah, elements. Okay. Any other ones that stand out to you that you really have no idea? You can practice them this weekend and let me know too on Tuesday. Okay? All right. Let's check time. We are right at the very end, so I'm going to go over one more thing and then we will pack up, okay? All right. I will have my plan is to try to get this set up. If it's not there Tuesday, it'll be there Wednesday. I would like you to see each of these, including chromatography. I will make you guys learn chromatography. I learned the hard way last year. So you guys will learn chromatography and you'll understand what's going on. It has to do with your solubility rules. So if you don't know your solubility rules, look them over before we talk about this, okay? It has to do with solubility rules because things that are going to form precipitates are not going to move. Things that aren't forming precipitates are going to be the ones that actually move through the columns. That's what it all comes down to, okay? So we'll talk about that more. We will do multiple proportions, definite proportions next week. You guys still have 2 minutes, so stop. Back you up in a minute. Stop.
Hey, you said 2 minutes, stuff plays.
Nope. All right. You guys are also behind, so stop. All right. So make sure you know your different families by this point. Okay? I think there was one question on your assessment. Did you guys get it?
Yeah.
Yeah? Okay, that's good. That's good. Make sure you got those. What I'm going to add to this is we are going to add your charges to copper, zinc, tin, antimony, lead, gold, and silver, and mercury, and iron, and chromium. Maybe manganese, I don't remember for sure. Nickel for sure. All right, so these guys are going to have, okay, these, if you circle those on your page, just write multivalent cation. And then you're done and you can pack up. Cobalt is too, but I don't think I forced you to memorize that one. It's either cobalt or chromium. I don't remember which one I make you memorize. What? Oh. So chromium, manganese, iron, nickel, copper, zinc, silver, gold, mercury, and those three. So there is an easy way to kind of memorize them. You find patterns. So if you want to look them up, otherwise I'll tell you.